Oh, oops. Give me a second. My camera is not connected. Very, very awkward. One moment. I'll be right back. I thought I tested everything before I started, but obviously I didn't.
Let's pretend that everything was okay from the beginning. Shh. Notice that you did not. Teaching you I am. I'm a professional. I have spent about 10-15 years as a professional software engineer and systems engineer. I've been teaching at a tertiary level for 5 years. So I'm a professional and I never make mistakes. Okay, my camera's on now. Just making sure stream is still healthy, everyone can see it. It looks like I'm still going out publicly, but just let me know. Yeah. So yes, I totally know what I'm doing. Hey, this goes back to like what I was talking about in my professionalism lecture. You can have all the experience in the world. You can think you know what you're doing and stuff like that, and then you can just like, I don't know, not plug your webcam in when you're about to stream. So yeah, that's my proudest moment. When I look back on 1511, I'm gonna remember that time that I went live on stream with my camera off, and that will be my fondest memory of my brutal displays of my own competence. Okay, can someone just say something in chat to make sure that I am actually back on and live? Otherwise, I will just be talking to myself here. Let me just see. Okay, good. Thank you, Izzy. Thank you, Sean. Thank you, Kat. Ah, back I am. And Tom's trolling me. Hi, Tom. Okay. So, today we are looking at recursion. So today's like a special bonus, in a sense. Well, it's not a bonus, but it's a lecture that I have not delivered before in COMP1511. So I shuffled a few things around this term to try to squeeze in this topic, and it's a topic that I find very, very interesting. Because we've seen a lot of technical programming, we've seen a lot of how to put things together. And this thing that we're learning today extends on the things that we've been learning previously about functions, and also what we learned earlier this week about stacks. So when we were learning about stacks, we learned that, as you add functions, they build up a stack of functions. And when a function returns, it goes back to the previous one in the stack. So there's this kind of order of the way things that are called and returned. And we're going to start manipulating that order and using the structure itself to make things happen. So let's get into it a little bit. So last lecture, Tuesday, we were talking about abstract data types. So this was us extending the ideas that we'd first introduced in multi-file projects, but going a bit deeper this time and learning about a specific example, which was stacks, and showing how we could implement stacks with arrays or with linked lists. And from the front end, from the implementation, in the main, you wouldn't necessarily know which one had been used, but you do trust the rules that are put together in the header file. We don't have a huge amount of time in the course to really delve into this, because next week's tutorial and lab are going to be wrapping up the course as such and giving you some practice for the exam and things like that. So we won't necessarily have time to go super deep into this, except in the assignment 2 you will kind of be going into this because it is an example of an abstract data type, but a lot of the work you're doing in the assignment is in filling out one of these rather than creating it yourself. So there's a bit of back and forth there. It's useful, and and it's the kind of thing you may use in the future. I always kind of talk to everyone with the possibility that a significant portion of you are going to be continuing on in computer science. And if you are doing so, then a lot of this stuff leads on into the future. Today, we are covering recursion, and recursion is kind of funny because we are using the program stack to do things, and we're using the idea that functions can call themselves. So it is a funny and interesting thing, because up to this point, we've never had a function that called itself. Because you can think of that, if a function calls itself, then when it runs the next time, it's going to call itself, and then when it runs, it's going to call itself, and you can feel like there's the possibility of this kind of infinite recalling of the same function. And it's similar to, we've done this kind of cyclic idea and concepts before. Like a linked list is a node that can point to another node of its own type. A function can do the same thing. But it gets more interesting with a function, because then we start to look at the idea of what happens when something calls itself, and how do we think about this? So those of you who are a little more mathematical in the way that you approach your programming, or you get into like this abstract concept of what's going on when you're programming, will probably appreciate this, because it's a very, very interesting way of coding, and it's going to flip the way we've been thinking about programming on its head. Because everything we've been doing up to this point is like, you do this, then you do this, then you do this. It's kind of concrete. You can watch the steps and go through them. But recursion flips it and just kind of does things in this weirdly backwards way. So it works really well if you get it. But it's one of those things that takes more thinking time and less coding time. So I think we did this a little bit with the linked list stuff, where we spent a lot of time drawing pictures, and we spent a long time drawing pictures and moving the arrows around and trying to see how the pointers move, and then we wrote like 1 or 2 lines of code. But like, it's still the kind of thing where you have to invest a couple of hours into the thinking about what you're going to do for those 2 or 3 lines of code. Otherwise, you don't really know what you're doing with it. And recursion's going to do the same kind of thing. So it'll be a small number of lines of code, but it'll still be like a great effort to kind of figure out what you want to do with them before you write them. So we've got examples today we'll talk through. I'm going to go through this at a basic level, because again, we don't really have the tutorial and weekly test support to cover all of this. However, it still might be useful. The example I'm going to use is going to use linked lists as well, so we're just kind of reinforce your knowledge of those things as well. Gira-chan says, I feel like this course is just teaching us different ways of getting stuck in an infinite loop. I would add to that, it is not just ways of getting stuck in an infinite loop. We're going to add not just infinite loops, but also infinite amounts of computer memory used, because we did that as well. Okay, so understanding recursion. So I've got this little meme here. It's easy to understand recursion if you already understand recursion. So I'm going to say, now that you understand recursion, you can use recursion. And you're like, what? And in order to understand recursion, you must already understand recursion, and it's good that you knew recursion before we start. This entire slide is a big joke, but I enjoy it. What we're going to get into today is the idea that recursion is kind of inverting the way that we think about programming. So if we think that programming is going to kind of go backwards like this is actually how we're going to be doing recursion. We're going to be setting up, in a way, an inverted loop structure. So I just wanted to throw this in because I thought it would be funny to talk about recursion as if we're actually doing recursion. And so recursion's got this kind of funny inverted way of thinking. So we'll go into this, but let's step through an example, and I'll show you an example of something simple to begin with, and then we'll build it up into something more complex. So if I asked you to add up all the numbers in a linked list, I would hope that everyone can do this by now. if this code is super confusing to you, I would say go back to, is it lecture 13? The first lecture on linked lists, where I showed you this loop structure, where we have a pointer to the first node, and we could move through the nodes by saying, I'm going to move that pointer to the next node, and so on as I go along, and I'm going to stop when that pointer is equal to null. So that's me going through a linked list, one element at a time. And this one in particular is just going to say the total starts at 0, and for every node I see, I'm going to add their data to the total. So I haven't even got the node struct in here, but you can tell that it's a basic linked list node structure. So if I asked you to add up all the numbers in a linked list, you could do it like this, loop through, go one at a time, and look at each one. So that's a given, and that's the way I've been teaching you so far, is that if you ever want to do something with multiple pieces of information, you just take one at a time and grab it, process its information, and then move on to the next one. But let's think about doing this in a different way. So we could define this mathematically in a different way, and we could even think about the way that this is coded in a different way. Oh, let me just move myself out of the way. So what about a different way of doing this is we use a function that can call itself. So I've got this function called SumList, which is going to add up everything in the list. And what it's saying is the total of the list is equal to the value that is stored in the head of the list, so the first element of the list, added to the total added up value of all of the rest of the list. So we say we're going to look at lists as a head and a tail now. And a head is the first element of the list, and the tail is all the other elements in the list. So I say the total for the entire list is the first element of the list added up to run this function again on all the rest of the list. So all the rest of the list should add up, and that should add up to the first one, and that should get you your total. So let's have a look at some diagrams to show how this is working. So I have this. The sum list is equal to the head's data plus the sum list of the next element in the list, which then gives us access to the rest of the list. So total is 10 plus, and then that's sum list, not add. I'm gonna fix that up here. I changed the name of it partway through my development of these slides, which you may have noticed I only just finished yesterday. They only went online yesterday. So we have the head here, and then SumList gets called again on this node here, which means what we're going to get is 10 plus whatever the rest of the list adds up to. We don't know what the rest of the list adds up to because we've called the function again, and we need to see what happens in the next one. Raymond, how it stops is interesting. We'll get to that in a moment. Good question, though. I always like when the questions are what I'm going to explain next in the slides. It means you're on the same wavelength. We're heading in that direction. So then let's talk about what happens when the function gets called the second time. So this was the first function call. The head's value plus the sum list of the second node, the head next. And so if we expand this out, this is another function call of SumList, which says the head 1 here. So I'm going to call them 1 and 2. They're not called 1 and 2 by your program. They're all called the same thing, but they're in different places in the code. So they're the same variable name, the same function name, but they're in different pieces of memory. So it is interesting like that. So I called them head 2, but it's not actually head 2. It'll just be pointers to this one and then pointers to this one. So the head value plus some of the rest of the list. And so if we expand this out for what it does, it says its head value, which is this one's value, plus the sum of the rest of this list. So what we then get is 10 plus 2 plus some list of this 5 node and onwards. So what's going to happen is this thing is going to move through the list, and it's going to say the total of the list is equal to the first element plus all the rest of the list. And then you call the same function on the rest of the list, and you say the total of this part of the list is the first element plus all the rest of this list. And you keep going. And we can do this for the third one as well. So we've got the first one's value plus the second one's value, and then another function call here. So each different color is another function call. And this third function call says, okay, we take the third value, and then we add its value plus the sum list of the value after it, and continue onwards. So you can see how this is slowly building up. 10 plus 2 plus 5, and then whatever else. So what we get is, because it's calling itself as a function, more and more of these function calls are piling on top of each other, but each one of them is taking one of the elements and its value and adding them together. For the moment, this might seem like a convoluted way to loop through a list. And loop through the list and just grab values. But it's more about the technique that we're using, though. Let's continue. And this is Raymond's question here. Raymond was asking, so it'll stop when it reaches null. And the question is this endless? And it feels like it is at this point, because what I've written so far is actually endless, or it will hit the end of the list and then it will basically crash, because this has said head data plus some list of head next. So if head happens to be null, at this point, head data is going to be the point that we will crash, because we'll try to access a field inside a null pointer. So this thing is kind of it's a runaway train at the moment. It's just going to keep making function calls, and we don't have any way of stopping it. So like anything that we've done so far in C, anything that's going to do multiple things similarly. So basically all the looping that we've done before, I always said to you, anytime you start a loop, you want to know how to make it stop. That's going to be the important thing. So what we need to do here is think about how we stop recursion. So the questions are, what happens if we reach the end of the list? This was Raymond's question, so it'll stop when it reaches null. Actually, Raymond's question was much more nuanced than that. Saying it'll stop when it reaches null means you were actually asking both of these questions. So if we reach the end of the list, or if the list was empty to begin with, we need to know how to stop. So we need what we are going to call a stopping case, where the function won't continue to recur, so it won't continue to keep calling itself. And so let's set up a stopping case like this. What we're going to end up with in a recursive function, and this is something that we're nearly always going to have in recursive functions, is two options: stop or go. It's as simple as that, really. So the keep going case is something that we've already done. That's this one here, that says if we're going to keep going, then we'll take our head data and we'll call the function again. So the keep going case is usually going to call the same function again with some movement going forward of what's happening in what we're doing. But the stopping case is going to say, I'm going to stop and I'm going to return now. So remembering what return is, return's going to say, I'm finishing with this particular function, and then I'm going to say, I just realized this function doesn't work because it's meant to return an integer. Did I return something in the first one? I did. I returned the total in the first one, and I forgot to return the total in this one. So let me just... return total. I'll just fix that up now. I'll fix the box later. Alright. I'm going to wait for that bar to get out of the way. Okay. So, two cases. And we're going to test something to decide which of those two cases we're in at the moment. So, are we going to keep going, or are we going to stop? And we've got to figure out how we want to stop. So, the example is, if the list is empty, or we've reached the end of the list, if we're adding up the list, then we know that we could add 0, or we could say that the list is equal to 0 if it's empty, and we'll know that that's the point where we say, okay, we're not going to add anything more to this. So we could return 0 instead of adding stuff up with total. So if the head is null, so if we get given an empty list, we can return 0. And so we can say that if you gave me an empty list, the total of the list is 0 because there's no quantities in the list. Or you can say, if we got to the end of the list, then give back a 0 as well. Because if we're trying to add a null, so we're trying to add an empty element, so we've gone off the end of the list, we can say add 0 to the number you have, and you've already gone past and added up all of the actual numbers. So if you add 0 to all the actual numbers, then you'll still have your correct total. The trick also is in this stopping case, we are no longer calling the function again. David, you are correct. Is total outside of scope here? Yes, we should put that in here. Yeah, okay, I'll fix that up later. You can tell with the example code, I didn't actually copy paste out of code I wrote. The later examples code I actually wrote, this is code that I was just saying, I know that this is probably going to work. And that's the bane of all programmers' existence, of saying the phrase, I know that this is probably going to work, because chances are it's not. Okay, but the thing that we're learning about is the stop or the go. So when you stop, you would return something. And in this case, you're going to return 0. And then it's going to go back to the function that happened before. And then that's going to return its total, because it's got to return from this this line of its function, and that's going to return to the function that was previously running. That's going to return to the function that's previously running, and they're all going to cascadingly hit the end of this line and into the return and continue back. We'll show this in more detail in a second. So what we now have is the capability to have a function that can keep calling itself until a certain point where it says, I'm now complete, and I will stop calling myself, and then we'll go back and we'll finish. This structure of how these functions keep stacking up, I'm using that term intentionally, they keep stacking up all these function calls, is what I was showing about the stack earlier, and it's probably good for us to look at this in diagram format. So I've got a series of diagrams here about what's happening during the function calls of some list. So I'm just assuming that some list is of a certain size here when I'm doing this. So I have my main, and I make my first call to some list. So this is me just running this, saying, okay, I've got a list, please add up all the values in this list for me. It's like, okay, cool, let's start doing that. What then happens is, as the function recurses, so as it starts to work its way through the list, every time it calls itself, it calls another version of itself. So I've color-coded each of these so that you can see that even though they're the same name, they're going to call themselves again. So this is me saying the head plus everything else in the list. Everything else in the list is then this function call, and then it says its head plus everything else in this list. And this function call, as it goes further into the list and saying its head plus everything else in the list. So this is building up these calls. They're not exactly the same color. Maybe I should have, but they're not exactly the same color. But yeah, head plus this. And so each of these is adding up. And every time the function is called, a new function goes on the stack. So this new function has its own set of instructions, and it will be at a certain point in those instructions, and it won't necessarily be at the same point as the other functions. It'll have its own variables as well, so each one will have its own total that it's working on, and each one will be calling another function. So for every element of the list, we call another version of this function, and we get more and more and more of these functions. Anu's asking, if head is null and it returns 0, how do we ever get the total? Let's we need to look at how this is piecing things together, right? So, for example, say this one at the top here returns 0. It will return 0 to this function. It's not returning 0 to the main. It's returning 0 to this function, and this function will add 0 to its own head that it looked at, and then this function will give its total, which is 0 plus its own head, to this function, which will then say, okay, the previous total plus my head is the new total, and then it will return to this one. So let's actually just go on and see that. So as this one returns, so let's say this one was null, it will return 0 to this one. This one will then add its 0 here to the total it's building up, and so it'll be the head of its list plus 0, and it'll go, okay, that's the total, and it passes the total to this one, and this one then has a total from the rest of the list, and it will add its head to that total, and so on and so forth, all the way back to the main. So you get this building up of function calls, and then this kind of cascading return of function calls, and they'll all return through each other back to the main. And then what you get by the time you get back to the main is that every function call has added something to all of the other function calls as it goes through, and then they give all of that information back to the main, and then the main says, I've been given a single return. So I called a single function, and I expected a single integer back, and it gets a single integer back. But the way that single integer has been built up is out of this structure of building functions on top of each other, so that each function was going to do something on part of the list, and then they all come back, and it accumulates all of their built up work together in this sequence of returns all the way back to the main, and the main says, okay, now I have all of the information. So that, in a nutshell, is the process of how recursion works. And I have gotten to the break way sooner than I expected. This is what we get when I was counting the number of slides, because usually I talk about slides for roughly a couple of minutes each, and I didn't realize with all these diagram slides that there wasn't actually that much I was talking about here. So when you're getting a first run of a lecture like this, things can go a bit quickly. So I'm going to skip the break slide. Actually, maybe we will. No, there's not really any point in having a break now. Let's go into this and start doing some code. So I will go to the break when we get to midday. But I have a feeling, considering I've gone through the theory of recursion really quickly, that maybe I have not exactly planned the lecture time exactly. So this one might end early, but we'll see how we go. So let's do an example of coding recursion. So we're going to do some programming for this, but then afterwards we're going to analyze it and have a look at how it actually came together. So what I would like to be able to do is reverse print the names in a linked list. So this is going back to our battle royale. So let's say while we were doing the battle royale that we had before, every time someone was knocked out of the battle royale, we added them to a linked list. So what happened was, every time someone was knocked out, we put them at the head of the linked list, and the rest of the linked list just moves along further. So what we ended up with was a linked list of names, which was in reverse order of the order that they were knocked out. And so what we want to do is we want to print that out by going to the last element of the list, and then the element before that, and all the way through, so that we're reversing the order of the linked list as we print it out. This is a slightly contrived example because I chose something that was specifically very annoying and weird to do in a procedural way, but can be done reasonably in a recursive way. So we're going to build up the code for this. And then when we've got this kind of working project that works with either procedural or recursion, we'll start fiddling around with it and we'll delve deeper into how this thing works. So standard linked list node. This is the same one we used in the big linked list example, the Battle Royale, where we've got a node structure and we have a next. I think we called them player nodes in the code that we actually created, so we'll probably be using the same thing. I have some code I prepared earlier. It's in the lecture section on the website, and I've downloaded it as well into my VLab. So we're going to start with some code which is a copy-paste of part of the first linked list lecture that just builds up a list, and then we're going to look at reversing it. So, standard linked list node, and the way it was created was the first KO'd player is the first element in the list, and the second element gets added on as the new head of the list, so it just pushes the first player along, and the most recent person to get knocked out will be the start of the list. So we've got this list, but we want to print it out in the order of this one, then this one, then this one, then this one. And the way that we would normally loop through the list is in the opposite direction. So it's like, okay, how would we do something like this? So without recursion, I was thinking up a way of printing out a list in reverse without recursion. I wonder if this is one of the lab exercises. I don't know. Tom, is this one of the lab exercises? I don't think it is, but maybe it is. Either way, could be useful. Special bonus for the people who turn up to lectures and read them. You'll get a bonus for your labs if this is a lab exercise, but I'm not sure it is. Either that or it's already been a lab exercise. But what I might do, if I wanted to print out the reverse of a linked list, Gira-chan thinks it was a challenge exercise. Yeah, because this I would consider this a challenge because it's really, really fiddly to do. Oh, it may have been a tutorial exercise or something, but yeah. So what I would do is if I want to find the last element of the list, I might loop through to the end of the list and print out the name. But then what I might do then is like, okay, maybe I would keep a pointer to that element and say the next time I loop through the list, stop just before that element and pick the one before it, print that out, do the same thing again, print out the one before the marker point that I have, and then keep moving the marker point back up the list until it reaches the start of the list, and then say, okay, I don't need to do that anymore. So I've got some code for that here, but let's work through it. Let me log into VLab. Week 8 challenge was actually to reverse the linked list. We haven't done printed out in reverse. Also, the challenge was actually to reverse the nodes, which is harder than what we're doing here. Here we're just printing it out. So I guess that makes sense. This is better for a lecture example where we don't have quite as much time to write all the code. Where are we in lecture 16? Yes. So let's make sure, because I did the complete thing and I hope I've hidden that in solution. And we'll open this one here. Okay, so where we're up to at the moment, so I named it player here. So this is stuff that I basically copy-pasted from the linked list example. I know that I'm probably going to need to print stuff out. I know that I need memory allocation for linked lists. And I have some string manipulation because there's strings in there. So I've included those things. I have a single hash define here which says that there's a certain maximum name of length, which is this array that's going in here. So the longest name we're going to accept for this particular thing is 99 characters and then a null terminator. Raymond is saying, always been curious about this. Whenever we log into VLab, there's different numbers like VX5 or VX7 and so on. What do those mean? Yeah, I'll let Tom answer that. Yeah, they're different computers that VLab runs on. Because VLab is... How many people are we looking at potentially using VLab if everyone logged onto VLab at once? The entire school of computer science. We'd have about 5,000... I'm ballparking here, 5,000 people? I don't know if we've got 5,000 people. Maybe 3,000 or 4,000 people at once. All logging into VLab at once. We need multiple large computers to run all of that. So we've got that kind of stuff, like those, like when you see computers that are the size of a fridge, like those rack mount sets of computers, if you've ever seen those. We've got a bunch of those that run VLab, and so each one of those is like a separate physical machine. So each of the VXs, I don't know. I haven't never actually looked at the server infrastructure that we have at CSE, but I assume each of those is a separate computer. Oh, right, Tom's. It's more than I thought. It's 8,000 students in the school, and all of those students have access to VLab if they want to. So if all of you logged on to VLab at the same time, we would need some serious amount of computing power to handle that. Okay, so what I've done is I've taken the create player function, and this is the same thing that we did previously, where it makes a new player by allocating memory with malloc. It gives them the name that we've asked to give them, and it gives them the next pointer we've asked to give them. And I've gone back to the super simple way of building up a linked list, where you say this person's the head of the list, and then you say this person's the head of the list, then you say this person's the head of the list. So it's just building them up like that. So simplest way that I could to create the list, and then we're going to look at reversing it. So, in order to reverse this, I might, or not reverse the list, just reverse printing out the list. I might write a function called reverse print. Reverse print is going to need to know the list itself, so it's going to have a pointer to a player, and it's going to get given a pointer to the first element of the list. And so I'll call that player list, so that we remember that that pointer is not just a single pointer to a single player, it's a pointer to an entire list. And let's write this function. So go through a list in reverse order and print it out. So I'm actually sort of jumping back with the code here, and what I'm doing is I'm writing this not with recursion first. So I'm going to show you this without recursion, and then we're going to show it to you with recursion, and we'll see how they work differently. So I'm thinking what I need to do is loop to the end of the list, print out the last element. Won't always be last, so I'm going to use a trick here. So I'm actually just sneaking in some linked list teaching into this lecture, especially because now that I know that the theory part of the lecture didn't take the hour I thought it would, now I know I can write all this code and it'll be good. Move the last back one in the list, do it all again. Okay, so that's my recipe that I think I'm going to need for what I'm going to do. So I'm going to loop through to the end of the list, but I know that I'm going to move the end back one in the list. So I'm thinking that instead of saying that the end of the list is null, I'm going to make the end of the list a pointer that I can move through the list. So player pointer end starts off as null, because no matter what the list is, if it's empty or has any elements in it, I know that the end of the list is going to be pointed at null. But what I'm going to do is every time I go through the list, I'm going to move this pointer back through the list. What are you talking about? Oh, whether VLab is lagging. I don't think you'll ever notice whether server load is causing lag, but you will definitely notice if normal internet lag is causing lag. I think we talked to Guru-chan about this, because Guru-chan's connecting from the US. So you have a minimum speed of light data propagation, basically, across the surface of the Earth, is going to mean that minimum 100 to 150 milliseconds of lag. And if you've got 100 milliseconds of lag when you're typing, you'll see it. So you'll notice that you press a key, and there'll just be this tiny amount of time before the key press actually gets sent all the way to Australia, to our servers, and back to the US, and then you see it happening. So, yeah, it can make it annoying a little bit. Kirjan says, I type at 3 words per minute on VLab. Oh, auto test. Yeah, I think when we're talking about if the auto tests take some time, that's probably, you know what I reckon that's going to be is the further you've gotten into 1511, the more complex your programs are, and the longer it takes auto test to compile your program and run a bunch of stuff in the background and then tell you what the results are. Potentially. I don't know for certain, but I know that like DCC and auto tests do a lot of work on your programs. So it's actually compiling it in multiple different ways to test all of the things that might be going on, so that if you get any errors, we can give you the best advice possible. And obviously, the more complex your programs are, the more kind of time that we use. You won't notice that much, but it might be like half a second or something like that. And William's saying that the auto tests involving structure are a little bit slower. Yeah. So yeah, we'll get that. I remember when we were working with really large graphics engines like the Unreal Engine, when we would compile that, we would actually hit the compile button on something. So when you're doing something the size of a computer game, so we think about something that a program is like a gigabyte once it's compiled. We would often hit the compile button and then go make a coffee or something, or go have a chat with someone, and then come back in 10 minutes and see if it had finished compiling. And there are people who would we would actually spin up Amazon Web Service compute nodes to compile something across multiple computers at once, and then give back all the compiled code and put it back together on one computer. So I'm interested that you're actually seeing that in 1511, because I wasn't sure if people would see that or not. That the more code you write, the longer it is going to take to compile. And Tom's linked SKCD there. I'm going to assume SKCD is talking about waiting for compile time and stuff. Okay, Tom said, can you open that link on stream? Compiling, the #1 programming excuse for legitimately slacking off. My code's compiling. Hey, get back to work! Compiling, and they're like having a sword fight on office chairs, and they're like, oh, carry on. Yeah, so that kind of thing happens. I used to, a lot of the time when I was writing bigger programs like that, I used to play those little games on your phone that just have you kind of maintaining something. So you just press a few buttons and go, okay, just update these things. And then these timers will run for like hours at a time, and then I'll come back later and something will have happened. But those are the kinds of games I used to play while I was compiling. So every time I was compile, hop into that game, go, oh yeah, there's a couple of little things happening, put my phone away, and then come back and it's compiled, and like I can keep going. So yeah, I think that's everything for that. Yeah. All right. We weren't actually waiting for compiling then. We were just me talking about other stuff. Anyway, okay, so we've got our end pointer here, and we're going to loop until this end. So if we're going to loop until that end, we're going to need a looping pointer. And I'm going to say that is current. So we've used this kind of current pointer before. Oh, Ramen, Clash of Clans. I played Clash of Clans for a little bit, yeah. There's all those games that are like... The ones that are in the ads all the time, I'm just like... I actually played State of Survival for a while because I was so sick of the ads coming up all the time. And I was like, fine, I'll check it out. And I was like, yeah, it's okay, it's fine. I don't need to play this game forever, but it's okay. So, if we're going to loop through a list, we need to point it to the start of the list. So we're going to take the pointer we were given and assume that's the start of the list, and we're going to loop from this one to this one. So yes, this one is null at the moment, which is the end of the list, but we're going to loop through to it, and then we're going to come back to it later. So we're going to loop using our most standard linked list loop, except instead of null, we're going to go till end. So if current is not equal to the end pointer that we've got here, we keep going. So we're going to keep looping through to there, and current moves on. Note that the way that I'm programming here, note the way that I'm doing this, I know that all of this is going to end up in another loop, but I'm not thinking about that yet. I want to make certain parts of this thing work, and then I'll figure it out later where it's all going to go. So it's kind of like I'm gathering all my bits and pieces together, and then I'll organize them. Because you can already see that if I've got do it all again, this all should be inside another while loop. But I'll think about that once I've got this one bit of code going. So if I loop through to the end, my current will equal null when this loop finishes, which means for me to access the final element of the list and my current is equal to null, I will probably want to trail along a previous pointer. Starts off as null because if we're at the start of the list, the previous pointer is null. So we've seen this kind of construct before that I've used before, where I'm going to trail this thing along by saying it's going to follow the current. So the previous is going to follow the current, then the current's going to move along. So we've had this jumping pointers thing before, right? So we move the current, previous joins the current, current moves on. Then previous joins the current, current moves on. So this is this kind of loop. Raid Shadow Legends. And Raymond saying, is there a way to immediately access the node that's before null? And I think this is answering that question here, right? So what I'm saying is, in order to keep track of the one before the one that hits the null, I'm going to keep this previous pointer. We can also, if we want to, so there's an option here, Anu is saying, so instead of saying, while current is not equal to end, we could say while current next is not equal to end. We could say this one would stop the current on the previous node. The only downside of this one is if current is null, so if we've hit an empty list, then this thing is going to break, and so we would need to test for if current was null and if current next was not the end, or if current was not the end pointer and current next is not the end pointer. So there's going to be some complication either way. I'm going to go for the complication of carrying 2 pointers around because I think it's easier to think of watching the 2 pointers move than it is to think of this pointer moves and it checks the one that's further along. It's like both ways are going to work, but I tend to go this way because I think that it causes less confusion further along the way because you can see there's current and previous pointers, and so you'll kind of know where they are. And yeah, Girichan and David are having that conversation right now in chat where Girichan is saying, yeah, you can do current next is not equal to null, and David's saying, well, that assumes the current is not null. And then having to make that assumption means we have to write more code. Either way, we've got to write extra code for this because we're trying to trail backwards in something where we can't see backwards. There's another way around this as well that I will show you. We're not necessarily going to use this in this course, but it is a foreshadowing of possibilities in the future. So if I did something like this, then we turn our linked list into something called a doubly linked list. And you can see why it's doubly linked, because every node is linked in both directions. And this is a linked list that's made specifically for us to be able to move in both directions. If we wanted to, if we knew we were going to be reversing things a lot, then that would make sense. So we could link things in both directions and go reversing is the same thing as going forwards, but all we would do is we would have a loop going on previous pointers rather than next pointers. But we're not going to do that for the moment, because it's interesting to look at how this code works. All right, so if I loop through like this, I can say previous is now pointed at the element just before end. I was going to put it in quotes, but hopefully that makes sense that end, when I say end, I'm referring to that pointer there. So previous is now pointed at the element just before end, so we can print that out. I'll use an fputs previous name, I think it is. Previous name. And that goes to the standard output. If you forget how fputs works, you can always look it up. Could have used a printf here as well, especially because I'm probably going to need to use a... Oh, you know what? I'm going to be smarter than that. If it's only a single character, I can use putchar to put a new line on the end of that. So this prints out the last element. The last element that's just before the null at the end. Now we just need to think about this carefully though, because what if I get given an empty list? I will only print out the last element if it exists. So I'm going to check first. If previous isn't null, then I will print out the last element of the list. If previous is null, I'm just going to print out nothing, so I don't even need an else for this. So if it's null, then I print stuff out. If it is not null, then I am going to move the end back one in the list and do it all again. Actually, this is in here if it's not null. So the end pointer that was at the end of the list, and I'm one before that, I now want to make the previous pointer where I'm going to stop next time. So end is previous. Means that I should have a default that always draws these three boxes that I use for the linked list. There's my null. So my current pointer moved all the way along to the null. My end pointer is also pointed at null. I mean, it's weird when I'm pointing at something that's null, because null's not pointing somewhere. But you get what I mean when I say these are pointing at the same thing. So here's my current pointer, and the previous pointer, which is the one I've been working with, is here. This is the first time through. It looks like this, and we say end equals previous means I'm going to move the end here to point at previous. So if end moves to join previous, it comes here. And now we know that the next time we loop through this, because we're looping until current equals end, current will then point at this one. So second loop through, the current would end up here, and the previous would end up here. And then we would print out this one, and then the end pointer would move to this one, then we'd print out this one, and so on, until we end up with having printed out the whole list. Okay, so end is equal to previous, and then we do it all again. We'll put that in here. Which means doing it all again means we'd put that inside a while loop. I don't think my end pointer is going to be inside that while loop. I think these are, because this is part of the do it all again. Let's just set up my structure. Take all of this, put it all inside that while loop. And then I need to think about how am I going to stop this. If the end is the first element of the list, then I know that we've come back to the beginning. So the end started at the far end, and if it came all the way back, let's use its color. Once it comes all the way back to here, then we know we've already printed out everything in the list. So if I say, while end is not equal to player list, the start of the list, then we run all of this. And I think that that's all I need to do. However, I'm not entirely happy with this function. I think it's a bit convoluted and there's a whole lot of stuff going on. So what I'm going to do is I'm going to separate this into this and another function. So this, I thought this would be a nice opportunity to sneak this in while we're doing a bit of procedural programming before going back to the recursion stuff. I haven't done many examples of how I can get halfway through something and say I need to change this. So I think that this could be separated into two different parts. So I can have reverse print, which is the loop that goes through, and this is dealing with printing out multiple words. But what I can do is I have another function that says just print out the word that is before a pointer. Yes, Josh, you're right in saying that you thought I was going to do this with recursion. We are going to do it with recursion very soon. But I wanted to show you the difference between doing something like this in procedural and then going to recursion. So we definitely are going to do it in recursion. But I'm taking a slight detour along the way. So what I might do, I think I might want a player pointer as the output of this one, and say a function called print before. And what print before is going to do is it's going to take a pointer that's aimed at the list, loop through until we hit that pointer, and then print out the one that's just before it. So we've got a pointer to the list, and then we've got a pointer to the one that's after, and we're going to print that out. And what I'm going to do then is have the internal bits of that happen here in another function. So print out the node in a list that's just before after. Return a pointer to the node that we just printed. I'm going to take all of this, because I think most of this is the code that I need here. But I don't think I need all of it. So we're going to loop to the end of the list. So current is equal to player list. Previous is equal to null. End is now called after. Do we have end anywhere else? Oh wait, after is equal to previous. We don't need that anymore, because we're just giving back a pointer to the thing that we printed out, which is previous, even if it's null. So we're going to return the previous, which means that this can now say run print before using player list and end, and I'm going to say set end to be equal to print before player list. Okay, so I think that's going to work. I'm wondering if I need anything more in here, but I don't think I do. So what we're doing is loop through, call print before, repeatedly until end returns to the start of the list. Okay, so that means the end is going to be at the back end of the list, and it's going to move backwards until it's the first element. Alright, let's see if this works. Not super confident. I'm sure there's something that I've missed along the way. Oh, Josh, you feel that Recursive is going to be way cleaner? Yes. This is the reason. So I'm working you through. I'm intentionally working you through the pain of doing it the normal way before we get the nice way. But we'll see. Again, I'm gonna have to do some debugging here, I'm sure. And I know in the back of my head, this is different from the solution I wrote yesterday for this, and so it's probably different from what's in the slides. So I'm not sure of what I'm doing right now. So we'll find out what I've done wrong here. Oh, no. Okay, it compiled, which means I'm going to have to find out what I did wrong the hard way. Let's actually call it. I realize that we can't do any testing if we don't call the function. Reverse print the list. So different options that I'm thinking that might happen here. It could print out one name infinitely. It could print out things in completely the wrong order. Lots of different possibilities. Let's find out. Okay. That was the first thing put in. It worked. Okay. All right. Good. Good. It worked. We've hit midday now. So with this procedural solution to the problem in its current state, that's good. That's a good point for us to leave this and come back after a break, and then we'll do the recursive version. We're going to analyze this version first and then do the recursive version after the break. So where's my break time slide? Okay. Cat's like, we're all gonna get pranked and it's gonna end up like 3 lines with recursion. Maybe Cat, you may be seeing into the future. Sean says, can we do it in 1 line with recursion? Doing it in 1 line is very hard with recursion because there's always 2 stopping cases. Well, not 2 stopping cases. There's always a stopping case and a go case. And if you can get both of those to go in 1 line, which is technically possible, it can be done. I mean, it's completely... it's a really bad idea for me to do that because I'm trying to teach you how to code. So compressing my code into 1 line doesn't teach you anything. All right. So as we're getting near the end of the course, we're getting near the end of all the content I'm going to teach you, you're going to start thinking about what stuff I want to learn beyond what I already know. So I thought I'd put just one little break time slide up about this, because this conversation happened last lecture. Actually, people are saying, oh, what other programming languages can I learn? Where can I learn them? So there's a lot of online resources about this. And you can teach yourself a lot of different things to continue. So if you want to, you can kind of, I'll jump to this one here, pick an idea of something that could be interesting to build. So you think about the way that stuff worked in the assignments. So it's like, oh, we could do this 2D grid, and we could work with this 2D grid to make things happen. Or we can do these kinds of complex linked list structures and things. If you want to, you can come up with ideas of things that you want to build. Excuse me. And play around with things that you want to do. One thing that you're going to get a lot of responses on is this thing called Stack Overflow. So I would consider Stack Overflow to be the largest sort of question and answer site online about programming. The only downside to Stack Overflow is you need to filter its content based on what you're actually trying to do. So I always like to joke about the different people that are on Stack Overflow. Some people are on Stack Overflow to show off what they can do. So they will give you that 1-line answer to your question that you don't understand. The other thing is, in programming, there are always multiple ways to solve every problem. Which means there are multiple people that think that their way to solve the problem is the only way, and everyone else should, I don't know, leave the internet permanently or something. You know, the way people sometimes act on the internet. So just bear that in mind whenever you're on Stack Overflow, that you're not going to get tutorials on Stack Overflow. You're going to get what I would consider snarky answers on Stack Overflow. That's the most likely outcome that you're going to get. So bear that in mind. But also, lots of free online courses. So people are talking about thinking about learning something else next. So learning Python or learning other languages, lots of free online courses. It doesn't have to be free online courses. If you want the solid structure and you want to get marks for it, there's obviously UNSW courses for a lot of these things as well. The stuff we do at UNSW won't necessarily be, here is a tiny portion of just learn how to write Python or just learn how to write Java or something like that. They're going to be, here is some deep and useful theory that will set you up for a lifetime in computing, and it happens to be using this language at the same time. This is what 1511 is, right? Like, it may be in C, and it may be a learn how to program in C course, but it's a learn how to program course in C. So what we're teaching you is a lot more of how do you actually think about programming and then do it in C. So, like, you choose. If you just want to learn a language and you already know a lot of the theory from what we've taught here, those free online courses are pretty good because you'll get through them pretty fast now with what you know about programming C. But if you want to say, like, I just saw Mark do this thing where he put 2 pointers in a node. Does that mean a node can link up to an unlimited number of other nodes? And the answer is yes. If you want to learn about what those data structures mean, what their ramifications are, and what continues on from that, you're probably better off doing a university course which really goes into the details of those kinds of things. So, you choose. But you can always teach yourself more. So experimentation is always going to be really good teaching. Okay, so let's go on break now. It is 12:07, so we'll come back at 12 past 12 exactly, and we will continue, and we will go from this procedural solution that I have into a recursive solution. I'll be back. All right, I'm back. Lots of interesting questions in the break, actually. A lot of people thinking about their future after doing COMP1511. Girichan, a very good friend of mine, did a similar thing to you with aerospace and then computer science. He actually finished his aerospace degree and worked in the aerospace industry for a while, but his partner was a good friend of mine who actually tutored her while we were both undergrad students. And we're still friends now. And she's big into tech, and just kind of like, as he like, at a certain point got a little tired of what he was doing in aerospace, decided to do a master's in comp sci, and now he works as a software engineer. So it's quite funny seeing how people jump around between things. Stefan's asking an assignment question. I don't think we can talk necessarily about assignment stuff right here and now, Stefan, but I think if you have specific issues, drop into a lab and ask the tutor there, or drop into a help session. Okay, so we were on break, and I think some of the best advice in terms of courses within CSE that you might want to continue, CSE Society is very good for that. I think they're putting together some resources on that. And general degree advice, I think the student nucleus is the best. Tom, I don't know if you've got links to all of those things. Oh, Shrey is here. One of the co-presidents of CSE SOC. Are you a president of CSE SOC yet, Shrey? I don't think you are yet, right? I don't know when the changeover is, but Shrey will be, or is already, one of the presidents of CSE SOC. So if, I know you've been voted in, but I didn't know when the changeover was. So yes, we have one of the co-presidents of CSE SOC right here and now. So he can probably give you links to any advice that CSE SOC has available on taking courses and what's in courses and things. The UNSW handbook obviously has some information, but that's a little paragraph. Sometimes you want to talk to other students about what each course was like. Get the lowdown on what each lecturer is like as well. The handbook is not going to give you gossip on what the lecturer is like and whether the assignments are hard or whether it's a wham booster or anything. I don't know if any of you were in the UNSW discussion group on Facebook, but apparently COMP1511 was voted for as a wham booster. And I was like, that's it. We're marking this course harder now. No, I'm kidding. I mark the course based on what I want to mark the course as. And 1511, because I actually know the statistics and the numbers, and I know that it's not a wham booster. I put a lot of effort into nailing Comp 1511's average right on the point where your wham averages are for everyone in the course. So I was personally offended when that came up as a potential wham booster. Unless it brings more people into the course, in which case I'm happy for that to happen. Anyway. Don't worry, Daryl, I'm not marking anyone. I'm not going to change my marking based on a random discussion on Facebook. I'm more professional than that, apart from not turning on my webcam at the beginning. Other than that, I'm more professional than that. Yeah, Tom, if we want to bring everyone into the course, we could just give everyone 100. That wouldn't be awkward at all, and a very horrible way to teach. Yeah. There's a weight loss course, which is a wham boost. Do you take the weight and shift it into the wham? Okay. So let's go back to this code here. And it was nearly an example of me showing, okay, here's some fiddliness. And you could see that I had this planned. So those of you who are saying, is he just going to punk us and then show that the recursion is much easier than this? So yes, this was exhausting. But let's have a look at what it was. So there's the outer loop that loops once for each element of the list. And it keeps track of the last element that was printed. So this is this outer loop here that says the last element. So at the beginning it's null, so there is no last element that was printed. And then it loops through and says, okay, print before this last thing, and then set the result of that to be the new last thing. So that's me saying, oh, there's a lot of stuff in this diagram right now. Okay, gonna remove this. Okay, so at the end of the first loop, the current went to null, and then the previous was pointed at the last node here. This was the end. I wonder if I can redo that. Let's see if I can play this back with undo and redo. I'm pressing Control Z and Control Y on my paint there, so we'll see if that works. So this was loop through until after. Loop until after, keeping previous as the node before. Okay, so when we get to this point, oh, hello. Someone just came to say hi. Supervising, making sure that I'm teaching properly. I seem to have her approval, either that or the laptop is warm, and so she just wants to sit near the vents of the laptop. Okay. So at this point, we have looped through, and once we've looped through, current will be after, once we've looped through, and previous will be pointed to the element just before after. This thing is no longer happening because we've split it out into a separate function. So previous is now pointed at the element before after. If previous was a node, we would print out I'm going to change my comments because my comments were based on this being in a larger function. Print out the name that's in previous. I probably don't even need to have that comment anymore now. And then we're going to return previous, which means that what we're going to do is once we've printed this out, we give previous back to this other function, and it changes end to whatever previous is, because print before is going to give us back the previous pointer. So if end becomes previous, I'll redo this. It worked. End moves to previous. Then if end is not the start of the playlist, so let's just, I'm going to call this PL, playlist. If end is not the playlist, we loop through again, so we call print before end, and current will reach the end. Let's do this. So on the second run, current will stop here, because as we see, if we put end into print before, current will stop when it reaches that pointer that goes into print before, which is the end pointer there. And then previous, if current stopped there, previous will stop here. And then we print this one out, and then end will move on to here, and we'll keep going until end points to the start of the list. So what we've had to do in order to loop through the list kind of once backwards is we had to loop through the list the number of times we have elements in the list. That's how many times we had to loop through the list. So it's a little bit of an exhaustive method for how to do this. Someone was asking me to go back through that. Sorry, just make sure who that was. Alfred. So hopefully, Alfred, that covers a bit more information about what's going on there. So yes, that was a bit exhausting, so let's try recursion instead. So when I'm putting together a recursive function, what I'm going to do is think about what's the stopping case and what's the going case. So the stopping case, oops, hit my mouse wheel. The stopping case is if there are no elements, we don't print out anything. So we can already see what our stopping case is going to be because we've kind of seen it already here to say that if previous wasn't null, so if previous is null, we're not going to print anything out. And we know that for a linked list, our stopping case is likely to be null as well. So let's just start a reverse. I'm going to start abbreviating this. I'm going to call it revprintrec. reverse print recursive, but I don't want to write that all out. So I'm going to say rev print rec, reverse print recursive, is going to take a pointer to a player list. And we're going to look at building this function up. Print a linked list in reverse. This is the recursive version. Yeah. David's got a response there for the function name. Reverse linked list printer using recursiveness. When the function name is over 80 characters, you know that you've gone a little bit overboard. Remember, the rules for naming anything is that it clearly says what it does, and also distinguishes it from the other things in the in your program. So if I didn't have one that was called reverse print, I would just call this reverse print. But because this is recursive, I'm adding on the thing to say it's recursive. So just because we've got two in the same program. So, stopping case. If the list is empty, we would stop. My going case would be... okay. So anytime I look at a list, if I want to print it out in reverse, I know that if I'm looking at the start of the list, just make sure I'm on camera. If I'm looking at the start of the list, I know that whatever's in the start of the list that I'm looking at is going to be the last thing that will be printed out. Because I know if it's reversed, everything before me is going to get printed out first, and then the head of the list is going to get printed out last. So, head prints last, the rest of the list prints out. Put this down here. Prints out before that. Okay. Start with a stopping case so that we know what we're doing here. If player list is null, that means my list is empty. Or, for example, I've recursed all the way through and I've hit the end of the list. Either way, if player list is null, I have nothing to print out. So if I have nothing to print out, I can return. And so I'm actually saying this is the point where I just go, okay, I'm just going to end this function. So it's interesting because I haven't used return very often with no value, no variable to give back or anything. But this is a case of me saying, I want this function to end here like this. So if I want this thing to end here, it's going to stop this function and say, okay, go back and we're done. Otherwise, okay, I need to put these comments inside where they're going to be. So I said the head prints last, the rest of the list prints out before that. So if I want the rest of the list to print out before the head prints out, I need to call that first. So I need to say the rest of the list prints out before I do, which means what I need to do is I need to call the reverse print on the rest of the list. So I say call reverse print on the rest of the list, then print out mine. So I've got some code here for printing it out. I don't have a previous pointer, so I'm going to need to print out something else. But I know that the thing that I want to print out is the head of the list, because I know I've called reverse print on the rest of the list, so this is the head of the list, which is the same as the pointer I've been given to the list itself. That's it. Oh, wait. I need to... Oh, no, I don't need to return. This is going to return automatically because it's a void. It'll hit the end. That's the code. And that's why I did the other code first. I was just filling time. I wasn't just filling time. But I wanted to show you the difference between... If I do this recursively, I give the computer kind of a blueprint for what it's going to do, and it does it. When I do this procedurally, I tell the computer what to do specifically. I mean, this is a very specific example because linked lists don't go backwards very nicely, but recursion can go backwards from something that could only go forwards. But this is all I have to do. We're going to need to pull this apart, though. We're going to need to pull this apart and look at this, because all I've done is written... What have we got? I guess that's one line of code. There's about 4. I mean, there's 6 functional lines of code. There's this, and that. Yeah. So what we did was we said, we're going to use the fact that if I pile things on the stack, they're going to come off the stack in the inverted order that they went on the stack. That's how I'm getting the reverse here. Because I put things on the stack, and then when they come off the stack, I print out their names. So only after things start returning, after these functions start returning, we're going to start printing out. So we've inverted our order just by using our function call stack. David saying, this is hurting my brain, but I see it. Yeah. So, this is why I saved some time. We've got half an hour left to talk through this. This is not something that I expect just to go straight into people's brains like this, because usually if I write this little code, it means there's more thinking that we need to do about how this works. Okay, so here's the same code. I don't know if I wrote it exactly the same. I think I did write it nearly exactly the same. Yeah. Girichan's response. Izzy had a similar response, but was like, yeah, this is good. But like, wait, is this it? Yeah. So recursion is one of those things that takes a lot of thinking and not as much code. So we had to think about this, but what we want to do now is we want to pick apart the order that things are happening. Because it's important to look at the order that things are happening, because if we don't look at the order of how this stuff works, we won't exactly understand. So I'm going to pull this apart with words and dot points and stuff so that we know how this is working. So, order of execution. These are, because it's so simple, there's only 3 lines. In a sense, there's 3 concepts. 1, check for stop in case. Otherwise, call the function itself, then print out your own thing. We could have made this smaller by putting these 2 print functions into like a printf or something like that if we wanted to. So these are the 3 things we're doing. We're checking if we're stopping. If we're stopping, we return. Otherwise, we're calling the function again with the tail, which is the all remaining elements of the list, and then we're going to print out the current head of the list. So we've got some questions here. People are saying, what if we want to print it in order? And then we can do stuff. So Trent's got a good idea there, is we might swap the order of some of these things to make them work. But let's see. I do actually, that is actually what I'm going to talk about here. So we're going to talk about switching the order, and so the conversation you're having right now, Trent and Girichan are talking about swapping the order of operations. I'm actually going to show you that. So I'm glad that you're talking about that now, because it's exactly where I'm headed with the same thing. So this is one call of the function, but this line here is going to call the function again. So, color-coded so you can see this clearly. One call of the function is in green. We check if we're stopping, if so, return. So let's just assume we're not returning for the first one. Otherwise, we call the function again with the tail, all remaining elements. This is the blue one now. The blue one says, check if we're stopping. If so, we return. We're not returning yet. Otherwise, call the function again with the tail and all remaining elements. This gets called again. Check if we're stopping. If so, return. So maybe this one's still not returning, but the one after will. Otherwise, call the function again with the tail, all remaining elements, then print the name of the current head of the list. So, the magenta one here, I want to say magenta, it's not quite purple. is going to print the third element of the list, and then after it returns back to the blue function, so it's going down the stack. So look, the stack is the indentation here. So this is the lowest thing on the stack, this is next on the stack, and this is the top of the stack. When this thing returns, we will then print the second name in the list, then this thing will finish, and then this one will print the first name of the list. So that's how we're getting our inverted order. We're getting the third thing first, then the second thing, then the first thing, because things are still happening in order, but this function doesn't get to finish until all the functions that it called and that they called finish first, because that's the way the stack works, right? The green is the lowest thing on the stack. We cannot get back to the green until all of the other function calls return. So that means that the printing the name of the first element of the list won't happen until all of the others are printed out. This is how this works. We should test this, actually. I should actually test whether this is... I'll just comment this one out. I should get the list in the order it is here, because this will be the oldest thing in the list. And Ang is the current head of the list. Oh, I probably should have grabbed the code to do a normal printout so we can make sure that these are reversing. But take my word for it. The list starts with Ang and goes upwards in this order. So if I get a printout that's the same order, top to bottom, as these lines, that should be correct. Alright, let's compile this. I'm actually not expecting mistakes here because I know that the recursive one, code-wise, is easy to write. Yep, okay, so the recursive one worked. And so this is why I didn't do that first, because it would have been like 3 minutes of coding. And then it would have been like, wait, how does that work? But that's why I did the other example first, so we can like really like delve into the data structure and see how this works. Okay, Rosie's saying, why doesn't reverse print recursion of the next print out the first element in the first, since player list is the first element in the list? Is it because of the stack? Yeah, it's because of the stack and when things get to do stuff. So, first function call goes on the stack, but it calls a function before it prints stuff out, which means that this function, the blue one, has to run, and it has to complete before the green one gets to run. So, the second one in the list will always print out its head. And remember that its head is not the same as the green one's head, because the green one said, I will call the function again with remaining elements, not the first element. So its head is the second element of the list. And again, when it calls the function again, only with the remaining elements, that'll be even more elements chopped off the front, and this one will print out its head. And so this current head is different every time, because it's its own head from when it was called. So, if we go back to the very beginning when I was showing you this, the first time the function gets called, this is the head of the list. Second time the function gets called, it got called on head next. So it's the next part of the list. Third time it got called on the head next of the second part of the list, which is this. And we're doing the same kind of thing, going through the list and calling it on the rest of the list there. And so now that we've gone through and seen how the stack works, we see that we get this kind of response out of this thing. So we see that every time we add something to the stack and we move on to the tail of the list, it's calling on a different part of the list. And then also that the returns happen, and if the print happens after the returns, we will print out only after we've completed the other things that we stacked up on top of it. Raymond said, can we change it to print in order? Yes, we can do that. And Unu's saying we just need to change the print statement. Yeah. So everyone is like heading towards this idea. So what happens? Sorry, just covering up. What happens if we change the order in the recursive function? So let's do this. We can check if we're stopping. So the stopping case is usually the thing we'll check first. because if we don't check for the stopping case first, we might always be running the rest of the function. We can get an infinite recursion like that. Recursion can keep going for a long time. The only limit on recursion is this one. So every time we do recursion, we add something to our memory use on the stack, which is a set of instructions that this function is going to follow. I think it is actually a pointer to where we're up to, and also all the variables that are going to get used in this function. We can keep building this up, hundreds of thousands of them, until we hit a point where we run out of memory. That's the sort of functional limitation of recursion. It's a pretty big ceiling. You're not likely to hit it unless you try to do recursion on, I don't know, chess. So if we try to do it for chess, we try to look into all possible futures of chess, and then we wind back. So we go forwards and backwards like that. So we go to the end of the game and we come backwards. And we could do that to try to figure out possible futures in something. That's one of the uses of recursion. We will definitely run out of memory if we try to do it for something as big as that, because chess is a branching future, so it's not even a single stack. It's like a branching stack, so things get really full on. But I think for our purposes here, when we're getting started, we're not necessarily going to be hitting a memory limit on it. Oh, Izzy saying, if we ran infinite recursion in VLab, would it just get killed? Thank you, Izzy. Let's do it. Okay. Let us remove the stopping case. Actually. There. And this. Okay. Let's just keep it running forever and see what happens. I'm pretty sure it's going to get killed. I think it's going to be the same as when we kept grabbing memory and nothing ever finished. However, I don't think we're going to get killed. I think the problem's going to happen when we run off the end of this list without stopping. But let's run it. I think it's worth checking. Okay, let's compile this. Yeah, Trent's saying it won't break because it tries to stab null. Yes. I love that you're using stab. Stab is something we say often as programmers for this arrow. So this stab this means follow this pointer and access this field inside this pointer. Oh, we have a warning here, and it's a good warning. And if you see this in your code, you should thank DCC for giving you this warning. All paths through this function will call itself. Warning infinite recursion. Yes. Yes. This is a problem. How are we going? Okay. Accessing a field via a null pointer. Trent was saying that. Won't this break because it tries to stab null? Yes, I think it will. Reverse print record player list next. So we tried to call player list next when player list is equal to null. So what we've done is we've gone through this list and every time we do it, we call it on playlist next. So we call it on less and less and less of the list, and we've gone all the way off the end of the list, and we've tried to use next on a null pointer. So we haven't necessarily, Izzy, we haven't necessarily got it killed because we didn't have infinite recursion. We had a loop that attempted to go off the end of a list. I mean, it is a loop that's trying to go infinite. But the only time it would go infinite is if it didn't move through the list. We can make that happen. Do we have time? We have time. We're going to make that happen. What happens if I don't go to the next and I just keep calling the function on the same pointer again and again and again? This might stack up continuously. So this thing, check this out. Reverse print record playlist memory location, playlist memory location, another memory location. So these playlist pointers are all aimed at something called at this. This is the function call stack. So there's our main, and then we called the recursive print, and then it called recursive print, and it called recursive print. So you can see that the point at which I failed, this is what was on our stack. These are the function calls that are on our stack. So it's exactly the same as that diagram I was having, where each one of these calls the recursive call on a different node in the list. So you can actually see these memory addresses. You can kind of see them moving through memory and calling the recursive print on a different part of memory. Okay, so let's see what happens if we just recurse forever. I'm gonna get that same warning, definitely. Oh, that was quick. Segmentation fault. Uninitialized variable accessed. That's an interesting one. How did we get a seg fault out of that? So, a segmentation fault usually means we have attempted to step outside of the memory that we have, and I'm not sure exactly how that happened. I think this... Oh, yeah, I was expecting something to print out, but nothing would print out because we never got there. I think this built up to the point where it was outside my memory. Yes, Shrey, that's true that this should have seg-faulted, but I'm just trying to remember why exactly. But I think this is just... we built up too many of these, and we have used up the memory allocated to functions, which is different from when we were killed from calling malloc too many times. It's actually a different part of our memory that we're using here. Yes. Yeah, that's what... yeah, Shrey's got it there. So, the function call stack, this thing, has a certain amount of memory that it can use. Segmentation fault means I've stepped outside of that memory. So this is something that you're probably not going to see that much, the segmentation fault, because we use DCC, and DCC gives us better errors. But if you're using the older compilers like GCC, you just get this a lot. And you get a segmentation fault, things dump you out, and they don't really give you enough information about what's going on. But yeah, I think that's what's happened, is we've put too many things on the stack, and we've moved outside of the area in our program that says this memory is for functions. And so it gets killed in a different way than the memory allocation. Memory allocation says there's this other chunk of memory for our program, which is where we put our variables, and they're slightly different, and so they actually die in different ways. Okay, let's return our code to the proper functioning state and continue the discussion that we were having. Yeah, Izzy, the function stack got big really fast. Like, I was expecting it to take a little while and then segfault, but I think that this was easy enough code to run that the computer was able to just stack up so quickly that the segfault was nearly instantaneous. Okay, so we had this and we were going to change the order. So if we swap 2 and 3, will the function behave differently? And there's been a lot of discussion in chat already about this. So let's try this. Let's take this recursive call and put it afterwards instead of before, which means that what we're going to do is print out the node that we're looking at, then look at the rest of the list. And then when we look at the rest of the list, they're going to print out what they're looking at and then look at the rest of the list. The stack is going to be the same. We're still going to be building up this stack and then coming back off it, because that's the recursion thing, is going to build up all the functions on the stack and then come down off the stack, returning from them one at a time. But this time, all the returns are going to cascade into nothing, because there's no code after the return. So in this case, the printing is going to be in the order that we build the stack, not the order that we come off the stack. So let's compile and run it this time and see what we get as printed out. We get this order. Now if we look at this, this is now the normal order of this list. So if we wanted a function to just print out a list, I can do a function to print out a list using recursion now. So this is a forward loop through the list. Is you do the thing you need to do on the current node, and then you call this on the rest of the list. If we look at this, this is the function here that I've just done where I've just swapped things. We're now printing in order, and we want to look at how we ended up printing in order. Let's look at the order of execution. If I do it this way, I check if I'm stopping, and if I'm stopping, I'm going to return. Otherwise, I'm going to print the current head of the list. So if I do the printing first, so I print the current head of the list, and then I recurse through the rest of the list, then call the function again with the tail, then this function happens after we've called it, right? Which is now after the printing. So this is now in this really kind of simple sequence, which is the way that we can, I guess, understand a bit easier. So we know that if we were going to read this top to bottom, we print the name of the head of the list first, and then we print the name of the head of the rest of the list here, and then we print the name of the head of the rest of the list here. And then when this returns, it will go back to this function, but this function has nothing else that it wanted to do, because this was the last operation that it did. So this returns to here, this returns to here, but they don't do anything else. So that's actually it. That's all we did, is we said, there's this function, but because we changed the order of things, we're still doing recursion. We're still going all the way up a stack here, and then all the way back down, but coming back down off the stack this time doesn't have any information. So we don't print anything else out. So what we get is this idea that the recursion's not always going to reverse things. We can go forward through them as well, and it depends on the order that we do stuff. So there's a lot of subtlety in here as opposed to the procedural programming. The procedural programming is not so subtle because it's like, do this, then do this, then do this. Really, really super exact. Whereas with recursive programming, it's like, if we do these things in a different order, it changes the way we walk up and down the stack. So if I put this back here, where it was before, now we're going to be going in reverse order, because we will be returning to this kind of functioning of the recursion. So it's very, very interesting. I think that's where we're at. So we are going to finish a little bit early today, but not exactly, because we still pretty much used our 2 hours. So another joke slide for fun. If you know recursion, you can return now. Otherwise, you can learn recursion by learning recursion. Sorry. Apologize for anyone if they look at this slide later and they're like, what was he talking about? And it's like, well, if you know recursion, then you know what I'm talking about. But if you don't know recursion, you have to return. Wait, if you do know recursion, you can return. If you don't know recursion, you have to learn. Anyway. So what we've seen is, we break this down into how it works. If functions can call themselves, that means they can build up a stack of themselves. They can build a stack of themselves calling themselves. Then that means that there's 2 orderings that we can use. We can use one ordering of the stack being built, or we can use the other ordering of the stack returning back through. And we can use either one of those to move through data structures or move through processes of doing stuff. So that's a cool thing about it. And it does have this interesting way of thinking about programming, because we think about, let's assume that this thing might be able to go forever and stop it. So like we think about how to stop something first, and then we think about how it moves. So it's a very, very interesting way of programming that you can see as like mentally backwards from the way that we've been programming up until now, which is why I'm only throwing this in at the end of the course, because I think that generally there's a lot more that you need to, that you'll probably just need to do with your procedural programming. but you can see how if you use recursion, there could be some interesting other ways of doing things. So I'm going to wrap it up there, a bit early today, but I think that it's just like recursion. It's really, really complicated, but it just takes less time. Yeah, I think it'll be interesting. If you want to, you can have a look at a bunch of your lab exercises and look at even just some of the simplest lab exercises and say, can I go back and redo this lab exercise doing recursion instead of the explicit looping through a list? And you may find that you'll have some really kind of elegant solutions to some of these problems through recursion. It won't always be like, honestly, this is a very specific case that I set up very carefully to go through a linked list in reverse, because a linked list really is a one-directional thing, because you've only got next pointers, right? So there's only one way it can go. So I set this up really, really specifically to show you that recursion could be a lot easier in particular cases. It's not always going to be like this. Sometimes the forwards way through is going to be easier, but knowing that you've got this other tool set might help you to work with different things like that. So another thing I wanted to point out here, I don't have slides for this, but Daryl's asking, can we use recursion in the assignment if we want? Yes, you can. I think that there are certain situations where it would work quite well. So I'm thinking, like, you have to add a playlist and you add it to the end of a list. You could use recursion to find the end of the list, because you could keep recursing through until you hit the stopping case, and the stopping case is where you add something, and then there's nothing in the going case other than a call. Like, there's no other stuff. So you could use it for something like that. Anytime that you need to look at every element of the list, you could use recursion for that also. I think it's a matter of taking what I've done here and seeing how you would modify what you do to make it work. Right. Okay, so the other thing that I wanted to say was that is actually the end of the technical content for COMP1511, in that I will not be introducing any new programming subject content in this course. Next week, what we will be covering is, as I was saying in chat at the very, very beginning, Devs React to speedrun of COMP1511, where I'm going to speedrun the entire course and say, okay, these are all the things we covered. So that should be a framework for your study for the exam at the end, because everything that I'm going to talk about in that will be in the exam in some way or another. I mean, there's some parts of it that I'm going to say aren't hugely in the exam and aren't entirely necessary. Like, we don't have the time and space in the exam to ask you to build an entire abstract data type, so we probably won't be asking you to do anything like that. We may still ask you to use them, and some of the theory in them, like this idea of stack theory and functions building up, is probably going to be somewhere in the exam. But again, it's not necessarily core, it's not necessarily necessary to pass. But if you're one of those people that wants to push your 90 to 100 or something silly like that, or you overachievers. I don't think I ever got any scores above about 90-ish when I was in my uni degree. But some of you are looking for those kinds of things. If you are, then stuff like recursion, stuff like stacks and things is something that you're going to want to know. I'm also going to talk about what's in the exam. So a lot of people have asked me little questions in the lead up to what's going on in the exam. I'm going to put a good hour into that to talk to you about exactly how the exam works, exactly what the question format is, what I think are the best techniques to get the best marks, how to effectively do an exam when you're trying to do it online from home and things like that, and the proper test conditions and things. So I'll be going through all of that next week. But here is the point at which I cut off and say I'm not going to introduce any new topics next week in the lectures. All right. Thank you all for coming along, and I hope that recursion has twisted all your brains around so they're backwards now, and you've seen the world from a different light, and I think that will be very interesting. I think that's actually a good point to end COMP1511 on. So what I've done I hope, for everyone is shown you how you can code. And so everyone can do some basic programming now, but you can see out the door. And from out that door, you can see this wide world out there that I just showed you. The tip of the iceberg of. Okay, I'm mixing up my analogies here. Out the door to the tip of the iceberg. Yeah, you can see the future, right? You can see all the possibilities that we might take our programming to, and how you could potentially get there. So I will wrap it up here. And I will just go into break time for a bit, and I'll come back afterwards. And if anyone has any questions and wants to go further into Recursion, or you want me to poke into any of the code that I've shown you here today, I can do that in a sec. All right, back soon. I'm back. I thought I might also just... I don't know how well you can see that. No. She's actually sitting... She's made a nest out of my CSC sock hoodie, which is very cute. Because I wore the CSC sock hoodie for like the sort of end of winter that we had there. So I think it smells like me, and it's also cuddly. So she's like pulled it down off the chair and made a little nest out of it, and is sitting in it. So I think Chicken's representing my link to the student societies, which is nice. Girichan asking if Chicken codes. A previous cohort of COMP1511 started a legend that Chicken actually invented C, which is why C is called C, because it's named after her. Alright, do we have any questions about what we're doing? So if anyone wants me to go through any more detail about Recursion, or talk about the code that we did here, I think it's quite funny that we went through this procedural version of it. So Nace is asking, if it's a void function, where is it returning to? This is an interesting look at this, right? So the void function may return. What it's actually doing is, this return is finishing early, this return is finishing when the function completes. But this is the line in which the function is called. So at this point here, when this call of reverse print recursive is finished, it will then pop to this line. So it'll say, I'm finished here, now go on to the next line. And then it will go on and do this other stuff. So when you return, you go back into the other version of the function at the point at which we stepped out of this function. So we can consider any time that a function call is made, we step out of the function we're in, and we start a new function, which happens to be with the same set of instructions, but it's a new function. And we start running here until we get to this point. And then we step out of that one into another one. But then when we come back we'll come back exactly where we last left off. Void just says that we're not giving any information back, but it doesn't change the location that we turn up to. Yeah, so hopefully that answers that question. Ramen saying, I forgot to do weekly test 9. Do all of them go to our final mark? Not necessarily. I think there are 7 weekly tests, and only the best 6 out of 7 are counted. So you always get one freebie. Having said that, it was due yesterday. You could still do it if you want to. We might still mark it. Like, sometimes we're nice and we'll still mark things even if they're a bit late, especially with weekly tests and labs. Like, for us, weekly tests and labs are things we want you to do. We don't really care about necessarily assessing you on those things. They're for you to assess yourself, which is why there's only a very small amount of marks. When we care about the variation in marks, then we put stuff in assignments or the exam. The marks that are in the weekly tests and the labs are just something to tell you that these are things that we think you should do. And, like, it could nearly... Like, I could be very happily... I could run this course and say that everyone gets full marks in labs and weekly tests if they submit them. You know, but then I'd get people submitting blank files, which would be really silly. But what I'm trying to do is basically give you marks so that you put effort in on those things. And if you put effort in on those things, then you get the serious marks in the other parts of the course, because putting the effort in those things directly correlates to getting marks elsewhere. So yeah, it's kind of like, if you're gonna do it late but still do it, I might still give you marks. Yeah, and as Kat's saying, one test is 1% of our final mark. I think it's even less, right? Because 6 tests add up to 5% of your final mark. But as Kat says, I'm really happy when people say stuff like this. Just do it anyways. It's good practice for the exam. The weekly tests are good practice for the exam. And Josh is saying, best 6 or 7 count. So that's been in the course outline. But I understand that not everyone reads the course outline, or even if you did read the course outline, you may not remember it, because it may have been like 3 months ago that you read it. Or maybe 2 months, but still. Yeah. Yeah. Okay, I'm assuming at the moment that there are no more questions, just because no one has asked any questions about the code here. So I have a feeling that everyone knew, because I think I said it in the weekly notice, that week 9, the content was useful, but not necessary. So I think everyone who's like under the thumb and looking at the marks is probably working on the assignment at the moment, rather than wanting to learn about this other stuff. I mean, it's helpful for anyone who's continuing on in computing, though. So Raman has a question. Go for it. Random is fine. Which library is random in? Standard library, I think. Oh, I wanted to I wanted to talk about like some funny things where you could just randomize the output of your code. And then run it repeatedly against something like an internal version of auto tests until it answers all the auto tests correctly, and say, okay, this permutation of the randomness of what we did is the one that we submit. I would love to see someone do something like that. Okay, so Ram's saying, notice that I don't really use fput or fgets that often. Is that bad? Can't remember when they're more useful than printf or scanf. I would say that if you only want to learn one of those things, fgets is the one that you definitely want to learn. Because fgets says I grab an entire line of text. It's something that scanf can't do. So you got to be careful with that. Because scanf %s is super, super dangerous and you should never use it. Because scanf %s doesn't have any guarantee for how big the array is that it's going into. So it could try to overwrite off the end of the array. I think. I can't remember because I just never use it, because I know that there's fiddly stuff with it. So fgets is the one that will grab a whole line, and it gets you all the spaces and all the other silent characters that scanf won't get you. Fputs. So if I was to comment this out and say the following, I'd get the same response, right? So this is one line that does the same thing as these two. I'll leave it like this so you can see that I'll see the in the demo code you can see this. So this, you don't necessarily need to know either of these. You can get away with printf for those. But if I want to read in a whole line, then fgets is super useful. Yeah. And as Josh is saying, scanf is going to, if I try to do scanf with a string, it's only going to take one word. It's going to stop at the white space. But either way, I would just avoid scanf with %s because it's potentially dangerous. Yeah, so there are some cases. I would say printf versus fputs and putchar, you'll get away with only printf. Because even if I wanted to split that up and do it that similar way, so a string and a character, and have this as a /n, I can get all the functionality out of putchar and fputs out of printf. I probably won't do that. I'll just put the new line in there. Yeah, so you can get the same kind of functionality, but taking input, fgets does something that our other pieces of code, like scanf, can't do. Also, getchar is super useful because if you want to eat a line, one character at a time, and just go through until you hit something specific, you can do that. So getchar, if you grab them one piece at a time, you can do things like read a line and read words and then put those into strings, and then read numbers and put those into, and pass those into integers. So you can actually do this kind of back and forth where you grab bits and pieces. Scanf can kind of do that as well, so long as everything's separated by spaces. But scanfing with words is a little bit fiddly. So hopefully that helps. Alfred's asking, I want to ask why I code int previous is equal to null and use the if function with that and previous not null. Will it give a runtime error rather than skip it? So you're testing if previous is null, and then you're doing some. Let me just copy this code for a second. So you've got this kind of thing where let's make a previous pointer, and you set it up as null. So we didn't need to set it up as null, but assume that we've got something like that. And then you have an if statement or a while loop, and you have something like this: previous next is equal to 1, and previous is not equal to null, and you're wondering if this is going to cause a problem or will it give a runtime error. So this code here will cause an error because actually next equal to 1, that doesn't make any sense. Even if I do this, okay, this is definitely going to cause a runtime error because previous is null and you're trying to look at the next of a null pointer. If you're trying to access a null pointer, we did this earlier, I think, when we're accessing a null pointer, we will get an error. However, everything in an if statement is done from left to right. It's not exactly, because there's the ands and ors, there's order of precedence is most important, but then when we've got an and, we will test the left before the right, and if the left fails the test, we will not test the right. So we can flip these around. So I could actually say, if the previous is not null, then check the previous next. This will be fine, because if the previous is null, this AND will fail without ever looking at the right-hand side of it. So if you have this situation where you think it might be null, and you have like a stop in case if it's null, or another stop in case if something inside it in one of its fields means something, you can always test it like this. And this should be able to run without any particular runtime errors. I mean, there might be something else in your code that's causing an error that manifests here, but this kind of layout here will work, where you can know it's guaranteed that the left one will be tested towards the right before the right one if you've got an AND like that. If you've got an OR, they both have to be tested, because actually no. If you have an OR and the first one is true, then the second one won't be tested either. So that same kind of thing where you can go left to right like that. Josh is asking if we can use extra includes in the assignment. Yes, you can. You can use any libraries you want. So I think what could come in handy? The C-type library could come in handy if you're looking at individual characters. You can't submit extra files, though. So we have our submission set up for specific files. So if you wanted to start making your own abstract data types, we don't accept those, unfortunately. So we've got to do it within the files that we've got. So that was Josh's question. Yeah, so you're thinking of C-type, totally. Yeah, you can use it. I think the only limitations we have on the assignment is you don't bypass the linked lists in the assignment and use arrays instead of that, because we've already tested you quite thoroughly on arrays and we don't need you to prove that you can use arrays again. So if you were to make the library point to an array of playlists and the playlists have arrays of tracks in them, then we'll have a problem there. I think most of our auto tests and things will spit the dummy if you start using arrays in that way in the assignment. So Stefan's asking, wondering why in the given prototype files of weekly tests, the data in the given structs are always indented with a really big space between int and data. I'm not sure, Stefan. So this is awkward because I don't usually have time. I look through the questions and make sure they're appropriate, and change a few of them sometimes, but I don't usually look at the code itself and do all the code for the course. So I'm not sure, but hopefully it still all works and it's an accidental tab in whoever wrote the starter code. But usually it doesn't matter too much because C ignores any white space that's in our files. For example, this still works as the same C. It's really bad because it looks really ugly. It's really hard to read, but this C will still work like this. So I think that's probably just a typo in the master prototype file that's propagated through all of them, maybe. Raman's asking... Oh, Josh is saying it makes the variable names line up. Yeah, so sometimes when people are doing multiple variables in a row, they line them up column-wise so that everything's like really readable. So here's all the types, and here's all the names across. And so that's it. It's not a typo. It's actually it's a particular style. But as you can kind of tell, you could probably assume this because the course is way too big for only one person to have written all the content in the course. I mean, granted, I feel like I could, if I was given enough time, I could write all of the content for 1511, but I reckon that would take me 6 months or something to put a course together from scratch. It would take a long time. So it's written by a lot of different people, and so there's slightly different style and different things. So Raman's saying, why doesn't the main function actually return 0 if you do include it in the end? So if I do put return 0, actually whether I put return 0 or not, oops, little bit of VLab lag there, whether I put it or not, it will still return 0. The thing about the main function is it's returning 0 to nothing. So it's returning 0 to the terminal, But that's not printing out 0 to the terminal. That's just telling the terminal that I finished with a code 0. So if the terminal had a way of capturing that, which you can do, but we haven't taught it in 1511. So we can actually call programs from other programs, and if we call a program from another program, then we could check that code afterwards and say that was the code 0 or was it something else? If it was something else, do we need to deal with that? So as much as I've said that they return 0 and we've returned different values when we're trying to give off different error codes and things like that, that's something that we're kind of doing out of the possibility that programs might call each other, but it's not necessarily used. Yeah, but Raman, when we're saying other int functions do return the value, it's because if we're calling an int function inside our main or inside something else, so this output, for example, then we are going to use it. Whereas our main functions at the moment, we're thinking of our main functions as a self-contained thing where when we reach the end, we pack everything up and throw it away. So we're finished with it, right? As opposed to this function here, for example, when this thing ends and it returns something, we're not packing it all up and throwing it away. We're going to keep running with other things. And so we are taking its output and using it immediately. Right. I think that covers everything that we're talking about in the aftermath of recursion. So thank you all for coming. I will see you next Tuesday. I can't remember which thing I'm doing first. I think I will talk about the exam first. Because that's something that people really want to know about. And then after that, we'll do the speed run of the entire course, and I'll just say one slide or 1 or 2 slides about every single topic in the course, and we'll talk about that and refresh everyone's memory so that you're ready to start studying for the exam. Okay, see you next week. Have a good weekend.